Hey everyone, John Fraser here. This is a re-upload of an earlier video I made, the first part of my Faraday's Electrochemistry series. This has to be one of my favorite projects, but I noticed a number of mistakes I made in the script of the original video, so I decided to unlist the original video, correct my mistakes, and re-upload a new version with those corrections. This video is that new version. I'm not going to take down the original, instead I'll just leave it unlisted. I'll link to the original in the description of this video. That way, YouTube won't spread my previous mistakes, but you can still watch the original and laugh at me if you'd like to see what exactly I changed. For this version, I'm going to leave everything but the corrections the same. So without further ado, I'll hand the video off to John from the past. This is litmus paper. You've undoubtedly seen it before. Chemists have used it for centuries to test acidity. As a quick reminder of how it works, if I dip this slip into a vial of acidic vinegar, it quickly turns the paper red, indicating an acid is present. Whereas if I dip another slip into this alkaline solution of sodium hydroxide lye, the paper turns dark violet. Now for the interesting part. If I dip a third strip into this vial filled with a concentrated solution of neutral salt water, not much happens. The paper just gets wet. But now what if I take the same wet slip of salty litmus paper and connect a battery to it? Almost immediately, blue starts to bleed from the negative lead, and more slowly, red starts to spread from the positive lead. It's almost like the electricity has somehow turned the salt water into both an acid and an alkali. Or perhaps it's revealed the hidden acid and alkali that were always there. This is the strange phenomenon the famous chemist Michael Faraday termed electrolysis, or electrochemical decomposition. In this video, which will be the first of at least 2 on the subject, I'm going to be building a simple tabletop device for rearranging matter using this phenomenon, so I can make fun and useful chemicals for my workshop, as well as talking about the device's strange history. In the next video, I'll be experimenting with the unique capabilities of some of those chemicals it can produce, and we'll be delving a little deeper into what the device can actually do at a chemical level. To build my electrolysis cell, I'm going to try to make use of materials and techniques that would have been common in Faraday's time, with some small exceptions which I will clarify when we come to them. I'm going to start by making a frame from these firewood-sized hunks of paulownia wood. If you're a long-time subscriber, then you'll know I like to use this wood, as it's nice and easy on my tools, and is plentifully available as an invasive species where I live. But just about any kind of wood could work for this project, and it's fairly small, so it doesn't need much. These devices can range from very simple to very sophisticated. For my purposes, mine will be a sort of middle-of-the-road device, not as simple as some, but certainly not as complex as others. What complexities I have added, I genuinely think contribute greatly to the safety and functionality of the device, as opposed to the more simple versions. This design is meant specifically for the electrolysis of chloride salts, like sodium or potassium chloride, but also to be easily modified for different substances. Importantly, I'm designing this device to be used outside, so I want to make sure it's sturdy and stable enough to stand up to the elements without fear of damage or of tipping over in the wind or anything like that. Electrolysis was discovered in the late 1700s, coming hand in hand with the discovery of the electrical battery, or voltaic pile, as they were called then. The ability of electricity to deconstruct and reconstruct matter at a chemical level revolutionized the field of chemistry. It's hard to overstate the significance of this phenomenon, but I don't think anyone says it better than Faraday himself in this excerpt from his experimental researches on electricity, where he says, "The extreme beauty and value of electrochemical decompositions have given to that power which the voltaic pile possesses of causing their occurrence an interest surpassing any other of its properties. For the power is not only intimately connected with the continuance, if not with the production, of the electrical phenomena, but it has furnished us with the most beautiful demonstrations of the nature of many compound bodies, has given us several new combinations, and sustains us with the hope that when thoroughly understood, it will produce many more." To have it in Faraday's own words, the man who invented the electric motor, that he thought electrochemistry surpassed all other uses of electricity really speaks to just how capable this strange phenomenon is. Reading those lines is really what made me realize I would definitely need to try some electrochemistry for myself. If nothing else, just to try to understand what it actually is a little better. Electrolysis typically revolves around polar chemical substances, because batteries or other electrical power supplies are able to create polar electric fields. They end up interacting with polar chemicals in many diverse and interesting ways. Faraday's researches in electricity covers electrolysis in great detail, and according to Faraday, there are two distinct kinds of these electrochemical decompositions. One being what he calls primary, and the other being what he calls secondary. Primary is when the electricity itself is responsible for breaking apart chemicals and turning them into their constituent matter. For example, electrolysis of molten sodium chloride table salt might make pure elemental chlorine gas, a constituent of table salt. We really owe our periodic table to primary electrochemical decompositions, as they were responsible for successfully separating many elements for the first time in the early 1800s. Primary decomposition was used by Sir Humphrey Davy, Faraday's predecessor at the Royal Institute of London, to discover a wide variety of elements in their pure form, the first of which being potassium metal, which he created through the primary decomposition of molten potassium hydroxide. Secondary decompositions are more complex and occur when two or more chemicals broken apart by electrolysis combine into an entirely new chemical within the device. Breaking down how these secondary decompositions work really deserves its own time, and I'll talk more about these in an upcoming video. I can't say for certain, but in my opinion, I think it was these secondary decompositions that really excited Faraday the most, because they're what led to many entirely new chemical compounds being discovered. As I wrapped up the woodwork for the frame, I thought it might be cool to try to ebonize the wood for this project. This is a wood staining technique I just recently learned about from the Mountaintop Joiner Shop's woodworking channel, which I'll link to below. The goal of this stain is to make the wood as dark as ebony, but to work, I'm going to need to generate a chemical metal complex inside of the wood called iron tannate. This is an old oak tree that was destroyed by lightning. All around its base are hunks of bark which have been thrown clear. Oak bark is rich in tannic acid, which I can extract just by boiling it into a tea. It seemed appropriate to use tannins from a tree with such an electric past to make the stain for my electrochemical device. Once I have my beaker of oak tannin tea, I switch over to dissolving iron filings in vinegar. Vinegar, otherwise known as acetic acid, can react with iron metal to form a water-soluble iron complex known as iron acetate. It makes for a beautiful ruby red solution, which I honestly couldn't stop staring at. Once I soak the tannic acid into the wood, I'll apply this solution on top. The tannic acid is able to steal the iron atoms from iron acetate and will form dark black iron tannate within the wood, as well as reaffirming the acetic acid or vinegar. The tannins on their own are a good stain and give the wood a nice oaky look. You can really see where the word tan comes from. After this coat is left to dry, I'll apply the iron acetate. One of the most fascinating things to me about electrochemistry is how rapidly it developed after the discovery of voltaic electricity. Electricity in itself is a bizarre phenomenon. Obviously, lightning has been known for all of human history, and knowledge of producing static electricity and related phenomena are attested to in written records that date back at least to ancient Greece. Aristotle's successor at the Peripatetic school, Theophrastus, wrote in his book on stones, which I'll link to below, about various minerals that could exhibit static electric effects. The word electricity itself derives from the Greek word for amber, electros, which was rubbed on rabbit fur to produce similar static electric effects. As far as chemistry goes, lightning itself is a natural source of electrochemical decompositions. Lightning creates what Faraday would call a secondary decomposition in the air by ionizing atmospheric nitrogen and oxygen, which then combine. When this nitrogen oxide interacts with rainwater, it forms nitric acid, which falls as a kind of acid rain. The acid produced is extremely dilute, but it is measurable. The 16th century alchemist Michael Sendivogius wrote on using rainwater for its unique alchemical properties in his Novum Lumum Chemicum. He appears to associate what he calls the vital force rain has received from the air with nitric acid salts. Sendivogius writes cryptically, and whether or not he actually observed nitric acid from lightning storms isn't really clear, but it is a distinct possibility, and would be an interesting example of chemists before voltaic electricity making use of the electrochemistry that occurs naturally. Some of Michael's later followers, the Sendivogian alchemists, were so convinced by his writing that they believed rainwater contained half of the secret to the philosopher's stone they called sal nitrum. Some would collect and concentrate huge amounts of rainwater, which they would sometimes call, and I'm not making this up, cloud juice, earning them the nickname of rainwater alchemists. Faraday would have used platinum electrodes for most of his electrolysis experiments, but I lacked the funding of the Royal Institute of London, so this is going to be where I substitute in much less expensive modern materials. For the positive lead of my electrolysis device, I'm going to use graphite. Faraday used graphite all the time. That's not really all that modern. But for the negative lead, I'm going to use titanium, which is very modern. Both are commonly sold as rods for welding purposes, and that's how I got these. I want to maximize the surface area of my positive electrodes, because it's at these electrodes that the secondary decomposition reaction I'm interested in will occur. One titanium rod will suit for the negative electrode, but the trick there is I need it to sit evenly between my graphite electrodes so that the fields between all of them are about equally strong. Next, some copper clamps will hold everything in place and give a spot to clip my alligator clips to. Returning to our lightning alchemists, Faraday himself was able to directly demonstrate the ability of lightning to generate nitric acid, and claims in his researches on electricity that wet litmus paper held near a static electric machine for a long enough period would turn red with the acid produced in the air, and that paper was afterwards explosive, as the nitric acid developed is a potent oxidizer and converted the litmus strip to flash paper. Despite alchemists like Sendivogius doing their work in the 1500s, electrolysis wouldn't really become an intentional practice until the late 1700s with the advent of the chemical battery. As Faraday mentioned in his quote from the beginning of this video, batteries, aka the production of the electric phenomenon, are inextricably linked with electrolysis. The two are sort of opposite sides of the same coin. The first chemical battery was a frog leg. It was in many ways similar to the potato batteries you may have made in school, but a little more gruesome. Luigi Galvani, who worked with the effect of static electricity on frogs, found that a wire of brass connected to a wire made of another metal, like zinc, both in contact with the leg, could result in the leg twitching, as though electricity was passing through it. Originally, it was believed this electricity was the product of life, but Alessandro Volta showed that an electric current could be produced if the frog's leg was replaced with a slip of cardboard soaked in salt water. This was the first voltaic cell. The salt promoted the water's ability to oxidize the metals. Because zinc is more reactive and easier to oxidize than brass, the salt water will oxidize it faster. Oxidation involves stripping the metal of its electrons. Because the zinc releases its electrons more readily than the brass, an unbalanced charge occurs between the two metals. That charge difference would come to be known as voltage, in honor of the man who undoubtedly saved countless frogs. What I find so interesting is that almost immediately thereafter, it was found that running electricity through salt water could create chemical reactions, just as chemical reactions in salt water can create electricity. This is where electrolysis was truly born, as an offshoot investigation after somebody discovered something strange that happens with frog legs. This is what really gets me about science. Rather than being a linear progression, or even entirely intentional, it's often the result of bits of this and that here and there, and what makes it what it is isn't a small collection of geniuses, or the result of impeccable philosophy, but more so, just the process of checking each other's claims. With everything I need for the device prepared, I place the beaker I'm using as a reaction chamber on the frame, and a smaller beaker with concentrated salt water within that chamber. The vessel is sealed to prevent the corrosive gases that will be produced from damaging the device. But for clarity, this seal should never be made airtight, and I included 2 glass tubes to promote airflow in and out in a direction downwind and away from the device. Now all that's left to do is to turn up the voltage using a direct current power supply, with the positive lead attached to the graphite rods and the negative to the titanium. As soon as the voltage is applied, the water immediately reacts as the charge cleaves it in half, releasing hydrogen gas at the titanium rod and oxygen at the carbon rods. Along with the water, the salt is also being split apart, and the constituent components of the water and salt are beginning to react with each other in solution, in one of Faraday's so-called secondary reactions. A few days later, and the water looks wildly different. It's turned black due to the physical erosion of the graphite rods releasing graphite dust. This graphite dust will be easy to filter out, but it isn't the only thing that's changed. A pH test of the black water reveals it's become alkaline. Along with this, there's a small amount of clear water in the outer beaker, which appears to have condensed from water vapor released by all the foaming and bubbling. Interestingly, when I tested this condensed liquid, I found the opposite change had occurred, and that this water was acidic. The electrolysis process is slow, so most of what I have is still salt water, which I will continue to electrolyze over the coming days, but I took it out and filtered it anyways. The chemicals produced in this reaction are much more hazardous than regular salt water, so proper safety attire is a must. I'll be able to show more of what I've actually made here in the next video once I have more, but as a hint, I'll show you this. Taking a litmus strip of each of my products, the acid and the alkali, I found that rubbing the ends together produced the evident smell of chlorine gas. Thanks for watching. I hope you enjoyed this video. It's me, present-day John, back again to close out the video. It's been almost a year since I originally posted this video, and embarrassingly, I still haven't made a video about using this cell. Don't worry, I promise this secondary decomposition cell will return. Eventually. I've got a really neat video lined up for it. However, I also want to look at some of the other electrochemical devices and experiments that arose out of this period. At the moment, I think the third installment of this series will actually be about telegraph batteries, rather than this cell, as that's the project I'm closest to completing. But we'll see what happens. These projects have a funny way of taking turns. Thanks again, and happy electrolysizing!